Hello dear friends. So in the previous lecture we looked at the introduction to indoor air pollution, and we looked at the common indoor air pollutants that we can encounter in an indoor setting. In this lecture we will continue further on the introduction. More specifically, we will look at the term indoor air quality, what leads to a particular indoor air quality, and also now we will start looking at the sources that lead to a particular or a specific indoor air quality. And as we know, this is a very complex situation. Indoor air quality is a result of many intercompeting or intercompeting influences or influences that act together with each other. So it can be anything synergistic or antagonistic. So after these many influences, we will arrive at a particular pollution concentration, and the influence can be the nature of the building, what goes inside the building, what is the purpose of the building, and the human activity. So if we were to look at it in terms of a flow chart, let us say once we start to make a building. So first thing is, okay, what is the building? Is it like a steel building with totally exposed material, or is there a coating? We are looking at the outside, but the argument applies to indoor also. Or is it a concrete? What kind of paints are we going to apply to the building? So we have the choice of building material with respect to the building objective. Hmm. So once we say, okay, we have such so and so building and we need so and so building material. So then the next thing is how to prepare that material. So we have our raw material. So we have the raw material, cement, aggregates. We have raw material, and then we need something to bind the raw material. So we have the binders and then some additives. Together we have raw material, binders and additives, and then we arrive. So let us say we add raw materials, binders and additives, and we arrive at the building material. This can be a panel or a slab, or even some furniture, let's say. Well, furniture is not part of the main structure, but the same argument can be extended to the furniture as well. Then we apply coating to this material. So here I am showing an example of a cafeteria. So let us say this can be just a slab, or there might be coating applied to the wall. Then here also we have the building material, or building furniture, and we have applied some paints or varnishings to make it last long. So we have to apply a coating, and then in coating as well we have binders, then we may have solvents, and we have additives. So once we are applying some coating, we probably have a powder and a solvent and some additives, and we apply the coating, and then this coating can also be a source of exposure. So we have the building material and we have the coatings, into all of which we have a raw material, binders and additives, and for coatings we have binders, solvents and additives, and together they will form a carrier of a building product. So basically these are the sources. Now the final building product, so a cafeteria environment, or a classroom environment, we have some sort of building product. Now this building product then leads to emissions. So here I am showing an example in which you have tables. Table is there, some cloth is there, maybe papers are there in the office, then we have the photocopier. So all these things can lead to different kinds of emissions. Can be particulate organic matter, inorganic matter, part of the dust, or could be from the coating which is applied on the building material, or from the wall. So this could be flame retardant, fluorinated compounds, brominated compounds. So these can be a source. Then we may have some binder adhesives being applied at different places, so these adhesives also can emit volatile organic compounds. And then we have also the contribution from the sunlight or the light and temperature in terms of how they drive the reactions that lead to the volatilization or emissions or the production and destruction of compounds within the indoor air. So here it is, basically temperature, humidity and daylight are then driving the emissions. They are incident on the chemical compound that has been used, maybe a solvent or a additive or a binder, and then they are driving the volatilization of a particular volatile organic compound from these binders, solvents and additives. So we have the raw material coming in, we have the building material as a result of material, binders and additives. Then we have applied coating. Eventually we have a building product inside building, and then the emissions are governed by the incident daylight, then the conditions within the environment, so could be temperature, could be humidity. So all these things are now leading to some emissions. But that's not enough. We have then the particular indoor air concentration, which also is influenced by the dwelling habits. So here I am showing another part of building material. So furniture with a sofa, and here I want to denote dwelling habits, meaning what is the activity in the room. Is it a office where people will come and sit and go? So when they are coming, one, people are bringing dust, and then the activity, the movement of people also then resuspends the dust. Similarly, when there is a sofa, then we have the coatings here, which may have, solvents will be there, additives will be there. So some VOC emissions, volatile organic compounds emissions will be happening. Same goes for the upholstery. Maybe the upholstery has been dyed, so that leads to emissions as a result of temperature changes or light incidence. Plus, when people are sitting and getting up, and you are moving the upholstery and the cushions, dust emissions will also happen. Then, since humans are involved, there may be, there may be some human influenced microbes being emitted, or through skin they are sort of coming onto the upholstery, and then when the next movement happens, these microbes will also get suspended. So this is how I wanted to show this room in terms of the dwelling habits. Then we have the loading and the air exchange rate. So loading, of course, it means what is the kind of activity we are looking at, how much is the air from outside coming in, which is bringing the indoor air pollution inside. So how much is the dust coming inside, how much is the chemical coming inside. So that comes our loading, the loading of the chemical or the indoor air pollutant to the indoor. But that's not enough. We have also to look at the air exchange rate, how fast, how fast it's coming in, and if the outside air is more clean than the indoor air, then the air exchange rate also freshens up the indoor air. So loading in terms of how much outdoor air is bringing the pollutant in, and if the outdoor air is a cleaner air, then how much is it cleaning the indoor air in terms of replenishing the clean air. But all of it is then dependent on the air exchange rate. A higher air exchange rate means if the air is cleaner outside, a higher exchange rate will make sure that the indoor air is cleaner. If the outdoor air is more polluted, then a higher exchange rate would generally mean that more pollution has come inside. So it's a conditional situation. The indoor air concentration in terms of outdoor is conditional on the outdoor concentration and outdoor settings. We will look at it more in the second week of the lecture series. So when we have this, we have so many things. We have the building material, the raw material itself, and the base material of the building. what kind of coatings come on top of this material. All of it is a carrier, and on top of the building products. These building products lead to emissions, which also are dependent on the temperature, humidity, and daylight, so sort of the meteorological conditions inside the room. All of these lead to an indoor concentration, which is also dependent on the dwelling habits, which is the movement of people, human activity, the loading from outside, and the air exchange rate, which is sort of telling us how much the indoor air is being replenished from the outdoor air. So in relation to buildings, indoor activities and occupancy depends on the type of buildings. So first, homes. In home we do too many different kinds of activities. So we have sleeping, cooking, cleaning, heating or cooling as well, and then in some cases there may be smoking. The occupancy is low in terms of only the inhabitants of the home will live. So if it's a nuclear family, maybe 2 to 4 people are living there. Even if it is not, then you will have maybe tens of people, but the home itself will be bigger. So when you are looking at a typical situation of one room or one bedroom or kitchen hall, bedroom hall kitchen bathrooms, the occupancy is relatively low, but the activities are much different in terms of they are sleeping, cooking, cleaning, heating, sometimes smoking as well. They are low occupancy when compared to the other types of buildings, which are our schools and offices, for example, which are very high occupancy conditions. We have like hundreds or thousands of people being moving in and about in these buildings. So in office, this can, if it's a desk work, it will generally involve working with computers, working with photocopiers, printers. People will use chair, but they may move about as well. You may have smaller cabins, or you may have large halls where many people are sharing the same hall, and a smaller cabin fewer people will be living, will be working in those cabins, and there will be a lot of movement around, because if it's a hall, then a lot of people will get up, move around. uh, in a smaller cabin, maybe the total movement will be less, but the air will be more constrained than a bigger one. Then we have schools. Schools, of course, you have studies where you have smaller classrooms and you have bigger lecture halls. So here also there are different settings, different exchange rates, in which how is the central ventilation, or are there how many windows, how many doors, are they open or closed, how well they are connected to the outdoor. Sometimes the lecture halls in classrooms will have doors, but they are opening to another indoor area, like maybe a common hall kind of place, and then corridor, and people are moving to different lecture halls within that indoor corridor. So the specific nature of pollution then depends on the conditions around that room or the lecture hall. Then school or universities as well, there will be sports activities. So indoor sports activities, there may be badminton, there may be gymnasium, um, volleyball courts, basketball courts, table tennis rooms, or table tennis halls. So we have different kinds of activities which actually occur indoors. Same will go to the universities. And then of course you have the dining rooms or messes, which are also high occupancy and maybe better looked at in terms of restaurants, but the conditions are the same, in that there is a lot of cooking activity happening in these areas. So the nature of pollution changes. So we have different types of cooking activities, maybe frying, boiling, steaming. uh, in restaurants you may have barbecuing. So different types of cooking activities and different types of emissions. And then when there is cooking, there is also cleaning. So cleaning of the common room or the kitchen area, so then the chemicals are being applied. Then we have fitness centers, which are gymnasium. Same, there may be in the universities and schools as well, where people are exercising a lot. So they are one inhaling and exhaling, and also they are sweating, and when they are doing the gym activity there may be abrasion and more release of human associated microbes. Then we have and again these are high occupancy. Then we have saloons where we have hair cutting happening, dyeing, drying, different kinds of activities are happening which would lead to emission of dust and also the emission of chemicals, because for example dyeing and polishing will have some organic compounds, and then you can sometimes smell also these volatile organic compounds. May not necessarily be very harmful, some of them, but depending on the material which is being used, maybe they are harmful. So these are different types of buildings, different types of activities, different types of emission characteristics, and different types of occupancy. So the whole indoor air quality in the building is as you can see now, a very complex situation, and generally one would need to look at them case by case individually. Depending on the setting of the building, you will have a different exposure and different means to approach this. So as an example, and we have seen this in the first lecture, we have the indoor air pollution source in households themselves. So in the, we'll go from outside and then go inside. So in the yard you will have trees or vegetation, so pollen will be emitted, and these pollens can go from outdoors to indoors, for example through windows, or a person is walking and carrying these inside. Herbicides and pesticides often are organic in nature, so some emissions may happen, so the emissions can go through windows, and a person is walking and then may take these if they are attached to dust, the person may take these indoors through walking, and then indoor resuspension may happen or some kind of exposure will happen. Then in an attic, especially if there are old materials around, we may have asbestos lining or asbestos sheets or asbestos pipings or things like that. Then attic, a place like attic is maybe not so often cleaned as well, so we will have more dust emissions possible. As soon as someone walks, maybe dust emission will happen. Then it may be a place where people store chemicals, and if the ventilation is not very high in attic, maybe it's the window is always closed in that kind of attic or a storage area, then the chemicals will build up in that area, so we will have an accumulation of chemicals. Then we have bedrooms where of course, like on the bed sheets or quilts or pillows, we may have dust mites, and if a person has pets, then also pet material can be there. So completely different characteristic from attic and the yard. Then in bathrooms, since the situation, the air is more moist, we have more relative humidity, there is chance for mildew growth, bacterial growth, fungal growth in the area. So again, if this is some kind of bacterial or microbial exposure being possible. Also in bathrooms, often people will store cleaners, so that will lead to more chemical emissions. So, or it will make chemical emissions possible. Whether or not they happen depends on the specific situation, but we have microbial and chemical pollution possible. Then same goes to kitchen, where we will have chemicals being stored in the kitchens. Then we have smoke through the cooking itself, and carbon dioxide, carbon monoxide emissions may happen. So different kinds of sources may happen within the kitchen. Then we have the living areas, where if there is a person who is smoking, then we have issues with tobacco smoke. Then as we have seen, there is carpets in the living area on the floor, so this will store dust or emit dust. Then we have furniture, so the chemicals on or the paints, they may lead to VOC emissions. And then we come to the garage, which is often a place to store paints and solvents and such chemicals, which will then emit chemical compounds. So even within the house, as we can see and as we have seen before, there are so many different micro settings and so many different types of emissions that are possible. So first we'll go to sleeping. People spend almost 6 to 9 hours per day across all ages around the world. There may be some specific cases where a person can sleep more or less, but on average, we can say people sleep 6 to 9 hours a day. So, studies have shown that indoor air particle number concentration, so the number of particles in a particular size base, let's say number of particles per meter cube, for example, of size 100 nanometers. So, we have more particle number concentrations of ultra fine particles, which are generally less than 0.1 micrometers or 100 nanometers. There is more concentrations of such particles and also of black carbon. So this could be related to like people turning in the beds and pillows, and the minimum is generally reached in such rooms during unoccupied periods. So it clearly shows there is some relation to the movement of people during the night as well. So maybe people are sleeping and there is less movement, the emissions will sort of slow down or lower, die down. But as soon as people move about, they will increase, and mostly related to black carbon and ultra fine particles. So what are the sources? The bedroom will contain emissions from furniture and soft furnishings. So furniture, again, paint, varnishing, so maybe some volatile organic compounds are there. Same goes for cushions and mattress, so some volatile compounds as well as the dust, and sometimes the cushions may be impregnated with flame retardant, some brominated compounds, and then they might also come through dust, and people may be exposed to them. So here it is, mattress dust, which may be a host of different viruses, organisms such as bacteria and fungi. Some inorganic dust might also be there, and then volatile organic compounds. So already through mattress dust we can be exposed to completely different kinds of chemicals, or completely different kinds of pollutants. Bedrooms are also sometimes characterized by lower ventilation rates than the others. So a drawing room maybe has more windows, and there is more chance of freshening from the outside air, assuming the outside air is cleaner than the indoor air in terms of the pollutant being in question. So, but in bedroom maybe there is one window, and maybe during sleeping a person can close the window depending on the season. And so generally sometimes bedrooms may be characterized with lower ventilation rates, that means less freshening up of the indoor air, assuming outdoor air is cleaner. And also we have so many bacterial or particle associated microbes, inorganic dust, and these pollutants can be risk suspended when people are moving around in the bedroom. And as we can see in the previous slide, the emissions lowered down where when the bedroom was unoccupied or during the sleeping hour. So the movement was lower, and as soon as there is movement there is more emission. So probably emissions of VOCs from furniture will remain the same, but things like people moving up and down or moving about on the mattress or on the floor will lead to more resuspension. Then cooking, so here is just an example of a stove. So cooking can be linked to an increased concentration of particulate matter, which is ultra fine fractions, fine fractions, and coarse fractions we have seen previously in terms of particulate matter, and we will see more what these fractions mean. So we have more particulate matter that can be emitted, and we can have more emissions of gaseous pollutants as well. So that can be carbon monoxide, nitrogen dioxide, volatile organic compounds, formaldehydes, and also a class of compounds known as polycyclic aromatic hydrocarbons. So cooking can basically again lead to particulate matter emissions as well as inorganic and organic chemicals. Then cooking emissions are of particular importance in sort of developing countries where people, or maybe not everyone, but a lot of people rely on solid fuels. and sometimes they are also using some inefficient cook stoves. So solid fuel combined with inefficient cook stoves can probably lead to more emissions of certain pollutants. Emissions from cooking is generally dependent on the type of fuel, gas, solid, liquid, the type of stove being used. Also, very importantly, what is the food that is being cooked and what are the ingredients in the food, the type of oil that's being used for cooking also, and the cooking temperature. So, right from the raw material to the cooking infrastructure to the cooking method and the cooking conditions, all these can lead to the different sorts of emissions from cooking. So when we look at the solid fuel that is used in cooking, this can be coal and this can be biomass fuels. And biomass fuels would be things like wood, cow dung and crop residues. Also, it is often reported that more or less around half of the world's households are dependent on the solid fuels. So again, wood, crop waste, animal dung and coal for cooking. And here there is a summary for different regions of the world, especially if we see Africa and Southeast Asia. Majority of the households have been using 60% have been using solid fuels. Then Western Pacific region 46%, Eastern Mediterranean 35%, and then sort of the American continent and Europe, they are using household the coverage of solid fuel is less in those areas. So we see a very wide variety of solid fuels being used, and we also see that mostly it is in Africa and Southeast Asia. And then we have indoor air pollution from solid fuels can account for more than 2 million deaths. So of course it's natural because we have a lot of population in these regions and a lot of households in these regions are using these fuels. So we have a lot of attributable deaths due to solid fuel use for cooking. Then we have non-solid fuels. Okay, this is an example. PM concentration solid versus non-solid. Particulate matter 2.5 concentrations in kitchens have been reported in the following order depending on the fuel that is being used. So when biomass is used, we have the greatest amount of PM 2.5 concentrations. Then if coal is used, lesser PM 2.5 concentration in indoor air. Then if we switch to kerosene, then the concentrations are even lower, and then when we switch to LPG and electric stoves, we have the least amount of concentration among all the fuels that are being used, among all of these fuels that are being used for cooking. Then of course this has been realized by different governments, and here is an example. In the 20 years from 1990 to 2010, 20 countries have managed to provide almost 1.2 billion people with access to non-solid fuels. So that is good because we have moved from biomass and coal to kerosene and mostly probably LPG and electric sort of cooking methods. And the greatest growth has been in India, China and Brazil.